All right, let's go ahead and go through these practice problems where we're going to do some titration problems here. And so if you take a look in a titration, the equivalence point is reached when 15.6 milliliters of 2.5 molar solution of hydrobromic acid is added to a 20 milliliter sample of an unknown concentration of lithium hydroxide. It's asking for what is the molarity of the base. What it's really asking for is the molarity of the lithium hydroxide. Because that is the base, that is also the unknown, and these types of problems are actually very easy. The first thing we need to do though is write a balanced chemical equation. We have hydrobromic acid, that's HBr. It is a binary acid because it's got two elements, plus lithium hydroxide, which is LiOH. Lithium is a one positive charge, so it only has one hydroxide attached with it. And it's going to make water and a salt, and in this situation the salt is lithium bromide. And the equation happens to be balanced. Now the question is, what is the molarity of the lithium hydroxide? And so there's two things we need to calculate molarity. We need the moles of the lithium hydroxide, and then we need the liters of the lithium hydroxide. And if you take a look, it actually gives us the milliliters, which we can just take the milliliters and change them to liters. But we don't have the moles of the lithium hydroxide. However, we can calculate the moles of the lithium hydroxide, and once we calculate the moles of the lithium hydroxide, we can take those and plug it into there. And so how do we do that? Well, what else does it give us? It gives us the liters, which we're given milliliters, but we can change the liters, and the molarity of the hydrobromic acid. And so we can take the molarity equation, we can take the moles of the hydrobromic acid divided by the liters of the hydrobromic acid. And actually, I mean take the molarity multiplied by the liters. And once we plug these values into this equation here, we can then solve for moles, and once we know moles of hydrobromic acid, we can convert it to moles of lithium hydroxide. So let's go ahead and do that. So we have the molarity, which is 2.5 molar solution of the hydrobromic acid. Then we have the moles of the hydrobromic acid that we are solving for, and then we just need to divide it by the liters, which is 0.0156 liters, because 15.6 milliliters is 0.0156 liters. And we just need to solve for moles now. And when you solve for moles, you end up with 0.039 moles of HBr. And so what this means is that it took that many moles of the hydrobromic acid to neutralize all of the lithium hydroxide. And then all we need to do is go from moles of HBr to moles of lithium hydroxide. And from the balanced chemical equation, it is a 1-to-1 ratio. So this happens to be 0.039 moles of HBr. Now again, once we figure out the moles of HBr, we can easily plug it into the molarity equation to where we have 0.039 moles of lithium hydroxide. We divide it by the 0.020 liters of lithium hydroxide, and this will give us the concentration of lithium hydroxide, which is a 1.95 molar solution of lithium hydroxide. And that is our answer. So just to recap, it was asking for the concentration, right? It's asking for the unknown concentration, and again, concentration is molarity. Molarity is moles over liters. The problem gave us the liters, but it did not give us the moles. However, we were able to calculate the moles, and then we plugged it right into the equation to get us the molarity, and it's that easy. Let's go on to the next one here. Okay, same type of problem. This time we have sulfuric acid being neutralized by a certain solution. Now this one's asking what volume of acid is going to be used in the titration. And so in this situation, again, we're going to be using the molarity equation. And in this situation, we're solving for liters, okay? So we're solving for the liters. And this is the liters of the sulfuric acid, because it says what volume of the acid solution. And so the question is, how many liters is it going to take to neutralize that much base? And so what we need to do is we need two things. We need the molarity and we need the moles. Well, the problem gives us the molarity, but we don't have the moles. It's the same thing as the previous problem. We can somehow find the moles of the sulfuric acid, and once we find the moles of the sulfuric acid, we can plug it into that equation to then solve for liters. Well, how do we do that? Well, again, we can use the molarity equation. This is going to be moles of lithium hydroxide divided by liters of lithium hydroxide. And we can use this equation to solve for moles of lithium hydroxide. Once we know the moles of lithium hydroxide, we can then convert it to moles of sulfuric acid, and then we can plug it into the equation. So let's go ahead and do that. The first thing we need to do is write a balanced chemical equation. So we have sulfuric acid, which is this, plus lithium hydroxide. Again, this is a neutralization reaction that's going to produce water plus lithium sulfate. Now to balance this, you balance the salt first. You put a 2 here to balance the lithium. And then whatever amount of hydrogens there are on the acid, that's how many waters you end up having. And that's how that works. So anyways, let's go ahead and do this problem here. So we've got 0.17 molar solution. We don't know the moles of the lithium hydroxide, but we do know the liters, 27.4 milliliters. All you do is move the decimal place over 3 times. You end up with 0.0274 liters. When you solve for moles, you end up getting 0.004658 moles of lithium hydroxide. I'm just going to put Li for lithium hydroxide. And then we're going to go moles of lithium hydroxide, 2 moles of the sulfuric acid. This happens to be a 2-to-1 ratio. And so when you type this in the calculator, you end up getting 0.002329 moles of H2SO4. All right, and then now all we have to do is take this here, plug it into that equation. What we end up with is 0.13 molar solution of sulfuric acid. We just calculated the moles as 0.002329. We don't know the liters. To solve for liters, you just take this and you take this and you make them trade places with each other to where the liters is equal to 0.02329 divided by 0.13. If you're unsure how to solve for the denominator there, just think of it as x and you're solving for x. But let's go ahead and type that in the calculator. And what you end up with is the amount of liters that you will need is 0.0179 liters. And a lot of times we measure things out in milliliters. This particular question isn't asking for milliliters or liters, but if you wanted milliliters, it would be 17.9 milliliters. You just move the decimal over 3 times. All right, let's go ahead and do this next one now. In preparation for a titration, 50 milliliters of an unknown concentration of lithium hydroxide So this is our unknown, is placed in an Erlenmeyer flask. The lithium hydroxide is titrated with this concentration of hydrochloric acid. And during the titration, the data is collected and is graphed below here. Based on the information in the graph, what is the pH of the initial lithium hydroxide? Okay, so this question's got a lot going on with it. First off, what is it asking for? All right, so I always think that's the first place you should be looking at. What is it asking for, and how do we get what it's asking for? Well, it's asking for pH, and pH is equal to the negative log of the concentration of the hydrogen ion. Okay, so it's asking for the pH of the lithium hydroxide though. And again, lithium hydroxide, when put in solution, produces this. So somehow we need to get this, from this. And again, from a previous set of notes, we can, if we can find somehow this, then we can calculate this using this equation here. Kw is equal to the concentration of the hydrogen ion multiplied by the concentration of the hydroxide ion. If we can somehow calculate this, we can figure out this. If we can figure out this, we can plug it into there. But how do we get this? Well, that is the concentration of the hydroxide ion. And again, concentration is molarity. Molarity is equal to moles over liters. And the problem gives us the liters, all right? So it gives us the liters. It gives us 0.050 liters, which is this right here, just converted to liters. And to calculate the molarity, which that's what this is right here, we need the moles. And to get the moles of the lithium hydroxide, we need to somehow use the molarity equation of the and use the molarity equation with the hydrochloric acid. Now, it does give us the molarity. So moles of HCl divided by liters of HCl. Now, in this particular problem, we're trying to find the moles of the HCl because once we know the moles of the HCl, we can then convert it to the moles of the lithium hydroxide, and then once we know the moles of the lithium hydroxide, we can convert it in, or we can plug it into this equation to then find the molarity of the lithium hydroxide. Because this is a 1-to-1 ratio, whatever the molarity of the lithium hydroxide is equal to the molarity of the hydroxide. And so once we find the molarity of the hydroxide, we can then plug it into this equation to then find the molarity of the hydrogen ion. Because once we find the molarity of the hydrogen ion, we can then plug it into the negative log of the hydrogen ion is the pH. Now, before I continue on, I want you to pause this video and I want you to really look at this process. This is sort of the beginning of this whole process, and then this is the end of the whole process. The other thing too is there is another pathway. There is another way of solving this problem, and it's the equal number of steps, but it's a different way. So I want you to maybe think about that as well. So let's go ahead and plug things into this molarity equation here. First off, the molarity of the HCl is 0.57. All right, it's 0.57. Next, the liters of the HCl? Well, we don't actually know. The problem doesn't tell us the liters within the problem here. It doesn't tell us the liters, but we need the liters. So where can we find the liters? Well, if you take a look here, we're given this graph, and we can determine the liters from the graph. If you take a look here, the equivalence point tells us the point at which the solution is neutralized, and this occurs at 25 milliliters. So you can see that it occurs at 25 milliliters, and that happens to be our liters, which 25 milliliters is 0.025 liters. So we do some very basic algebra to solve for moles of hydrochloric acid. What we end up with is 0.01425 moles. So I'm going to just do this, moles of HCl. And we do need a balanced chemical equation. We can see that moles of HCl is a 1-to-1 ratio with moles of lithium hydroxide 1-to-1. And then once we find the moles of the lithium hydroxide, we just plug it right into that equation there. And then once we plug it out of the equation, we just solve for molarity. And we have a 0.285 molar solution of lithium hydroxide. Now this happens to also be the concentration of the hydroxide because there's only one hydroxide within the lithium hydroxide. So this is the concentration of the hydroxide, which we can now plug into this equation here. And we end up with this setup here, and all we need to do is do some basic algebra to solve for this hydrogen ion, which gives us 3.50 or 3.51 times 10 to the negative 14. And then all we need to do is take this, plug it into this equation here, because the negative log of the hydrogen ion concentration gives us the pH. And we end up with 13.45, or a pH of 13.45. Now, and it really should be with sig figs this. All right, so now, and actually it shouldn't be, because the reality is this should only be 2 sig figs, which means that now that is the correct sig figs. All right, so this problem was quite a big one. So it was quite a big problem, and happens to be really problems I enjoy. Really what you're trying to do is you're trying to take the information it gives you, and you kind of got to work backwards to figure out how do I figure out what this question's asking for? How do I figure out the pH? And so we looked at the equation for pH and looked at, well, what do we need for that? Well, we need the hydrogen ion concentration. Well, how do we find that? Well, we know that Kw is equal to the hydroxide ion concentration multiplied by the hydrogen ion concentration. And the reason why we need to do that is because this particular solution does not have an acid in it. It has a base in it, which gives off hydroxide ions. And so once we were able to figure this out, then we were able to figure this out, because once you know one, you always know the other. And the way that we figured this out is how we figured out that in the other problems. So this was quite a long problem, but I think it really shows the process of being able to problem solve really well. So all right, let's go ahead and finish with this last problem here. I've already solved the first part of this problem, because the first part of this problem is exactly like the other problems that we just did. What I really want to focus on is how do we graph this curve. And so what's very important to, there's 3 things that you really need to consider when graphing a titration curve. You need to determine if the unknown is acidic or basic. If the unknown is an acid, you're going to start the curve somewhere down here, and it doesn't matter exactly where you're estimating it, just anywhere in this region. If the solution is basic, you're starting it up here. So if the unknown is basic, you're starting it up here. So that's the first thing. The next thing you need to do is you need to determine what is the equivalence point, and the equivalence point is the point at which the solution is neutral, and it's how many milliliters does it take to neutralize the solution. And in this particular problem, it took 45 milliliters of the titrant. All right, so it took 45 milliliters of the titrant. And again, because this happens to be a strong acid, strong base titration, that's going to occur at a pH of 7. And this here is about where it's 45 milliliters. So you can see it took about 45 milliliters, and again, it's a pH of 7. And so this happens to be the unknown happens to be a basic solution, so we're going to just start up here. And when you're graphing it, remember that it's going to be basic, basic, basic until it gets to the point at which it's neutralized, and then there's a drastic drop. And really, based off of what we see in this particular problem, this is actually all of the information that the problem gives us. But we are going to extend it as if they go past this point, because typically you do go past the point. And there's a lot of reasons why, because there's certain piece of information that you can get by extending it past the equivalence point. And so what will end up happening is, because we're continually adding an acid, we're just going to extend it down like that, and eventually it'll flatten out on the bottom into an acidic solution. Now again, this is an unknown base. If it was an unknown acid, this would be flipped. We'd start down at an acidic pH and work our way up there. But really, here's the key thing. This point needs to be pretty exact, all right? 45 milliliters, pH of 7. This point here, you're just kind of putting it, somewhere up in the basic area. If it was an acid, we would put it somewhere down here. And this is the overall way that you can graph this. Now, obviously, if it gives you the pH, you can plot the pH, the initial pH, you can plot that point. But if it doesn't give it to you, you just estimate what it is. And that is all there is to graphing. Definitely come to class with questions. Definitely review some of the practice problems and do some of the independent practice problems. Look at the answer keys, and have a great day.